All right, everyone. So I'm going to be talking about Lab 3 and reviewing it. And so Lab 3 was called Introduction to Waves. And in this lab, the first part was like you looked at standing waves on a string of metal beads. And then the second part was you looked at sound waves and then the resonance of different sound waves, which still look like sinusoids or sinusoidal functions. Um, but Uh, this is generally what a traveling harmonic wave looks like. So you have uh, these up and down. You have this up and down motion of the wave, and the width between the two crests, and the crest is like a peak. So the width between two peaks is called lambda, which is the wavelength. How fast the wave is moving to either side is called the velocity. And then the distance from the equilibrium point to a peak is the amplitude of the wave. And then waves also have frequency, meaning the rate at which a single point will complete one up then down motion. And then t is the period, which is how long that takes, and that's just 1 over the frequency. And so generally the velocity of a wave is just the wavelength times the frequency. Um, it's also, you can replace frequency with 1 over period if you want, but it's almost always written as lambda times frequency, which is fine. So there's two types of waves, mainly. So we have transverse waves, which move up and down. So the direction of the oscillation, which is up and down here, is perpendicular to the direction of motion, which is left and right. So obviously an up arrow is perpendicular to a right arrow, meaning that they form a 90-degree angle. So that would be called a transverse wave. And then the other type of wave is called a longitudinal wave. And that would be a wave that where the oscillation is in the same direction as the motion. So that'd be like a spring, because when a spring compresses, it's compressing horizontally, and then also the wave is moving horizontally. And so this is called a longitudinal wave. All right. And so I think this might be cut off a little bit. So let me move that over. There we go. And so the next part was that they just rewrote for you, or not rewrote, I guess they introduced the wave equation, which is like generally just, it's like a general equation that describes a lot about a wave. So in this term multiplied times x, which is a displacement, this is related to the wavelength. So this term tells you a lot about the wavelength of the wave. This term will tell you a lot about the frequency of the wave, and it's multiplied times time. And then this phi naught is like generally just a phase to the wave, meaning that we can start the wave off like halfway through a sine, or like a tenth of the way through a sine wave. And so it's not dependent on any variables like x or t. And then this y naught is the amplitude of the wave, which is like the height of the wave at the max peak, right? Or at a peak, or I guess the height of the wave at a trough. So the first part was you talked about standing waves, and so the important thing to know about standing waves is that we model them as the sum of two waves that are moving towards each other, and that also have identical properties, meaning they have the same wavelength and they have the same frequency or period. However, we can see that this negative here is different from this positive here, and that's what tells us about the motion of the wave. So if you have a negative here, then this wave's moving to the right, and if you have a positive, it's moving to the left. I know it might seem counterintuitive, but if you remember that for like a general like parabola, if you shift a parabola like 2 units to the left, that's an x minus 2 squared graph. Or sorry, x plus 2 squared graph. But yeah, my whole point is that this plus here means that we actually move it to the left, which is, I know, a little counterintuitive, but just try to remember that. And so the next part of the lab talks about how to find out at what wavelengths resonance shows up. Or I guess you guys hadn't learned about resonance yet, so maybe at what wavelength the harmonics show up. And so all they're doing is they say that at the two ends of the string here, this end and this end, or not this end, this end and this end we're going to assume that they don't move up and down, meaning that no matter what's happening to the wave, the y position of these 2 points is 0. And so they say on the left boundary condition, or the left boundary, we say that our displacement in the x direction is 0, and we're at time 0. So we plug in the parameters here, and we set it equal to 0 because that is our y position. Because like I said, remember at this left point, we're going to assume that it doesn't move up and down. I know this drive technically moves up and down, but it's moving up and down quite a small distance, so relative to the actual motion of the wave up and down, it's essentially 0. And so we just say that at this point it's 0, and then that means that no matter what, we can just set our wave equation to be equal to 0. Because remember, it was the sum of these two waves moving in opposite directions. All right, and so then the second part of the lab does the same, or second part of this does the same thing, where we instead look at the right boundary, or the x equals L boundary. And so in that case, at x equals L, what we can say is that we plug in 2 pi over lambda for, we're not plugging 2 pi over lambda, 2 pi lambda is there. I mean, we plug in L for this x value here, and we do that for both of these waves. So if we do that for both of these waves, and we plug in 0 for time, you'll find that they're actually identical. And so we still set this equal to 0 because we're saying that the y position is always 0. And then we end up finding that sine of 2 pi over lambda times L equals 0. And then we know that if we write sine of like x equals 0, we know that x is equal to n pi. And what I mean by that is that x has to be some multiple of pi. So n is an integer, meaning like n is 1, 2, 3, 4, ... like etc. Like n can be any integer, or positive integer specifically, and the sign is only 0 when x is some multiple of pi. And so that's all they do here. They say that 2 pi over lambda L has to equal 2 pi, or has to equal n pi. And then we solve for lambda, and that's 2L over n. And all that really means is that the wavelength of the different harmonics will decrease as we increase n. All right, and so this is what harmonics look like for a standing wave on a string. So essentially you have nodes and you have antinodes. So nodes don't move up or down, and then antinodes do move up and down. And so that's what you looked at. Equations like this are going to be what's really helpful for exams, I would say, because a lot of times you're just plugging in numbers and seeing what gives you the right answer, right? And so, for the rest of this part of the lab, you're just looking at different harmonics of the standing wave on the string, but that's not going to be super relevant for exams, I would say. And so then in the second part, you were looking at harmonics of like sound waves. And so it was really similar to the other part of the lab, or like to the first part of the lab, but you were looking at frequencies on the computer. So like you would pass in some signal like this, and then it would just give you like a histogram where, if this frequency is like 10 hertz, let's say, the histogram, like this peak would be at 10 hertz. Where like the x-axis is frequency. And then the y-axis was like, I think they called it intensity, which is essentially just like how loud a sound is. But you don't have to worry too much about, the nomenclature, the terminology there. And so you just went through and you measured these different frequencies of 256 hertz or of your tuning fork, either one, and you just looked at what they look like, right? So the more important things about this lab are the final questions, and that's like, what is a wave? So I think there's actually a really common misconception about what a wave is. So I feel like a lot of people think that a wave is like always sinusoidal, or it's like this up and down motion, and that's not actually true. So a wave is actually just a packet of energy that moves in space. And so what that means is that I could just like move, let's say I had a string and my hand was here, and I just moved my hand up and down one time. Okay, what that means is that in the string I like imparted some energy, and now the string looks like this. And what's actually going to happen is this is going to move down the string, and it's going to move over to the right, and it's going to move over to the right, or whatever, until it hits a wall, or loses all its energy or whatever. And so this is actually a wave. So there is no like up and down motion or like constant repetitive motion. All I have is one single peak, and this is still a wave, because a wave is really just a packet of energy. And when I say like packet, I just mean like some amount. And when I say energy, I mean anything that has energy. So like a peak has energy because you imparted energy into the peak to like create it, and that peak has motion. So a wave is really just a packet of energy that maybe is moving. Like we saw that standing waves don't actually have a net velocity, but you did have this motion up and down. And so that is movement, right? And so then the next part is describe the concept of wave superposition and what has it enabled us to do with waveforms. So really simply, wave superposition is just like it's just wave addition. That's it. All it means is that we can add waves. And so the important thing to know about this is it's not like it is combining waves, but it's even more than just combining waves. It's specifically adding them. So like I could say, oh, maybe I combine two waves by like multiplying them. But this is not wave. This is not wave superposition. You're just multiplying waves. If you want to say you have superposition of waves, you're specifically adding them. And so I think that's an important thing to keep in mind. All right, and then the next part was, how does your mathematical model of wave propagation fit in with your observations of standing waves in a string? So for this, it's like your model was probably similar to the model they give you, where it's like sine of kx minus omega t or something like that. And so, or plus, I guess it's plus or minus omega t. And so the whole point is that if you have a plus and a minus omega t, like two different waves, and you add them together, you'll get a standing wave, because we have two waves moving in opposite directions with otherwise identical properties. All right, and so then the last part is, how are sound waves and waves on a string similar or different? So the key thing here is that sound waves are longitudinal, meaning that they're due to differences in pressure. So you have this like compression and rarefaction. Rarefaction just meaning like the opposite of compression, so like pulling apart. So you have this compression and rarefaction of waves, and what that enables you to do is, or it's not that it enables you to do anything, but it that's just how the wave propagates, and that's different from transverse waves, like on a string, where they're, so as I said, they're transverse, and that just means that they move up and down. Like the oscillation is like up and down. But for longitudinal, we have like the wave looks like this. However, the important thing to know is that sound waves and string waves are essentially identical otherwise. Like you can still model them by like sines, and that's it. Like you can genuinely model them the same way, even though the actual like physics behind their motion is different. So they're essentially modeled the same way. So I guess just try to keep that in mind. But that's pretty much all for this review, and thank you.